So we go? Ready? Okay. Hi everyone, my name is Pabon and I work at Red Hat Storage, and I'm here with Humble.
Hi.
And we'll be presenting about how to use Gluster inside as a container and deploying it inside containerized orchestration systems. Okay. Now, before I continue, there's going to be a lot of information here. Okay. And you're going to feel like there's so much information you're going to not know what's going on. So just bear with us. We're going to go a little bit slow, and we're going to go into the storage parts as we go towards the end. But we have to show you a little bit of how the orchestration systems work, the technologies work, so you have more of an idea of how is it and why the decisions were made as we go forward. Okay? So here we go. So one of the first things that we did as we start taking storage and putting it in containers is, why are we doing this? Right? One of the things that we're doing is quite a few use cases. For example, the first one is administrators. What they want to do is they want to be able to provide their users with an orchestration system and for their containers. They want to provide also storage for their users for their containers, okay, as they deploy the applications. Second is that's to help the users from the administrator's point of view. Second, though, is that the administrators, they want to be able to manage these clusters using the same tools that they used to. And that's a big difference. They don't want to have a Kubernetes or OpenShift cluster, and then they want to have an OpenStack cluster, and then they want to have a storage cluster. They want to be able to use the same tools to manage everything: compute, network, and storage. Lastly, from the user's point of view, they don't care about any of those things, right? They care about, I want my app to run, and I want that much storage to run. I don't really care where you put it. I just want to make sure it's running. I want to make sure that the storage is attached to where I tell you to attach it, and I want to be able to run my app, right? And they want to do this simply as creating a text file and submitting it to the system, all right? So those are the use cases that we're trying to satisfy. So Humble, I'm going to pass it to Humble. He's going to tell you a little bit about the technologies that we use to satisfy these use cases.
Thanks, Luis. So good morning, all. So Luis gave an introduction about the use case we are exploring or targeting in the market, and the solution we are bringing to the market. Let's move on and see the technologies involved in the solution. We have mainly three components here. One is OpenShift, second one is Gluster, and the third one is Heketi. Let's start from OpenShift. OpenShift provides platform as a service infrastructure based on Kubernetes container management. So you mainly heard about three words here. One is container, the second one is Kubernetes, the third one is platform as a service. Let's start from the bottom layer, that is nothing but containers. Containers are the Linux processes or controlled Linux processes which host an application. But when it comes to an enterprise level or the cloud level, the application has to scale. Somebody has to monitor the application, and the application has to be highly available. So these are the kind of a job or responsibility of an orchestrator. In the container land, we have different orchestrators available, something like Docker Swarm, which came in recently, and we have Apache Mesos. We have Kubernetes. We love Kubernetes and we use Kubernetes. The third one is platform as a service. You would have heard about the cloud jargons like IaaS, that is nothing but infrastructure as a service, which OpenStack or AWS provides. On top of that, we have something called platform as a service. That is a PaaS offering. OpenShift is our Red Hat's PaaS offering based on Kubernetes container management. What PaaS provides in a cloud environment? It allows or it gives an ability for a developer to deploy an application without worrying much about the underlying infrastructure. He doesn't want to worry about what hosts my systems or things like that. He can just come and deploy the application. So let's discuss some more about the containers. Often it has been compared with virtual machines. I would say this is a misconception because, the VMs are based on virtual machine images and containers are based on the container images. But if you look at the left side of the slide, you can see that the virtual machine image consists of the applications and binaries or libraries required to run that application and a full-blown guest operating system with that. But if you look at the container side, you can see the application and the binaries and libraries required to run that application. But you don't see a full-blown guest operating system or an operating system in the slide. So you can see that there is a big difference between a VM and containers, but people call containers as a lightweight VM. So I would say that is a misconception. Moving on, we have one more layer called Docker. Docker is nothing but a container manager. What it does is, if I look at Docker in a different angle, it provides two things. One is setting up an environment to run a container, or it sets up a platform for running the containers in a standalone server. It also helps us to package the application in such a way that you package your application with the required libraries or binaries required to run that application. And Docker, after making the application in a continuous manner, you can create an image based on that, and you can keep it inside a public registry so that a client can pull that image and run containers from it. So if you look at this picture, you can see containers are control process. That's what I said some time back. So Docker sets up the environment for the container or a Linux process. It makes a controlled environment. That said, you have different blocks here. If you look at the C groups is a mechanism which kernel provides, where you can restrict the resource access of a Linux process. That said, if the Linux process has to be controlled in such a way that this much of the CPU share has to be given from the kernel, this much of the memory has to be given for the container, or those kind of things are achieved with the C groups. There is something called namespaces. Namespaces gives the local or isolated view of a global resource. That said, if you are running a Linux process or a container in a system, you have its own networking stack. So that has been achieved with the network namespace. There are mainly 6 namespaces available in the kernel. Unfortunately, one is missing there. That is nothing but user's namespace. But when you run a Linux process, it gets its own local networking stack. That has been achieved with network namespace. You have its own process tree. That has been done with the PID namespace. It gets its own file system. That has been achieved with the MNT namespace. So namespaces gives a local or isolated view for a Linux process, and you can run. Because of that reason, people think that okay, we are running in a VM environment. So what Docker does is setting up this environment. It also sets up the environment like security for setting up the SLN, XSecComp, and features like that. So this is one of the things what Docker does. But again, and as an application, we want to scale. We want to deploy. Docker helps us to deploy an application or a Linux process and host an application from a standalone server. But we have to scale, and the application has to be available in different nodes or a multi-node in a cluster. So an orchestrator does that. As I said, Kubernetes is our orchestrator. If you look at the Kubernetes architecture, you have master and worker nodes where you deploy Docker containers. Moving on to the next in the technology stack, we have Gluster. Yeah, so Docker also helps us to package the application, as I said. So you have application and binaries and libraries required to run that. So when Docker came in, people started to containerize their applications. So I was thinking why we can't containerize Gluster, because being a user space file system, we are the best fit to be containerized, and we have the advantage over the other traditional file systems. As we stay in user space, we are the best fit to be containerized. And we created a Gluster container image and kept inside the public registry of the Docker. So if you want to run a Gluster container inside a standalone server, it's similar as showing in this picture. You have to just download the Gluster image from the Docker Hub. Then you have to run the container with few options, or few options to the Docker run command. We'll come into that options. Before we move on, I would say that containers are stateless. It doesn't persist any data, or container images are immutable. But as an application, we want to save the data. So moving on that, we have an option what Docker provides us. That's something called bind mount. When you use an option like -v, then you provide a path from the host file system, then the path inside the container file system. What exactly it does is, it provides a host file system into the container. And when you store some data inside the container, it basically gets stored in the host file system. So the container goes down, the next container comes back, but it starts from an initial state. That is not something what we want, because we were part of a trusted pool before we dies, or the container dies. And we want to save the data, or we have to give a precedence for our metadata. our metadata mainly lies in varlib Gluster D. So we store that data inside the host file system using the bind mount option of Gluster. And Docker also provides a couple of other options for networking. Like if the container wants its own networking stack, you can make use of -net equal to none option, or you can make use of Linux bridge when you use -net equal to bridge option. But what we use is, or what we recommend is -net equal to host option. What it does is, it exposes the host networking stack to the container, so that as a storage appliance, we want maximum throughput in our network card, and we want to access, or we want to get maximum output from the network card. For that, we use -net equal to host option that allows the container to see the entire host networking stack inside the container. So this is one of the options we recommend, or put it as a best practice for running the Gluster containers.
One question here.
Yeah, sure.
So the first line basically, if you do it exactly like that with Gluster D, varlib, and so on, you can only have one Docker container per host, right?
Yes.
Yes.
Okay.
That's what we
Careful.
recommend.
Yeah, that's right. I mean,
All right.
moving on, one more option we provide when you run a Gluster container. That is nothing but we export /dev tree of the host file system to the container. Why we want that? Luis will take into that after some time, but we dynamically create volumes and we want access to the host storage. For that, we have to export the /dev tree of the host file system to the container, /dev tree of the host to the container. And then we just use the image what we just fetched from the Docker Hub. So these are the main options what we recommend, or we run when we run it in an environment. But when you expose the /dev tree of the host system to the container, we want to run the container in a privileged mode. But again, as an application, we don't have to stay inside a standalone server. We have to deploy our pods inside more than one nodes, and has to form a trusted pool and then export a volume. So again, Kubernetes does that for us. It's not that Kubernetes does all the job here. Rather, Kubernetes talks to the Docker daemon running inside these nodes and asks to deploy the Gluster containers from that. But again, these are kind of job of an admin. This is a kind of deployment thing what admin has to do in an infra. But looking at the PaaS offering, or a developer or a user, he comes and requests mainly three things. First one is, I want to deploy an application. As you can see here, you have some data about the application of a user. You have a container name that is like Nginx, and it has to be based on an image called Nginx. It has to expose some port or something of that sort. So this is an application. Application definition comes from a user. The second thing what user care about is a persistent store. I want 100 GB of space, as you can see in this schema. You have, I want to get 100 GB from your trusted pool, or sorry, not from trusted pool, but persistent volume store, and I want to get it mounted inside a particular path, so that when I write the data to user share Nginx HTML or the file system inside my container, it basically gets stored inside wherever the persistent volume claim refers to. So these are the three things what user care about. Once again, an application definition, which says that this is the data about my application, and I want the storage for my container, and it has to be mounted inside a particular path. This is, once the user put this request to the orchestrator like Kubernetes or OpenShift, what happens in the background? We have GlusterFS plugin inside the Kubernetes node. What it does is, it mount or fuse mount the volume inside the host where the application pod is running. Again, pod is just a representation of a container in a Kubernetes or OpenShift environment. It can be group of containers, but it has to coexist, and it has to serve the same application. It has to share the C groups or namespace settings of a process. So for us, it's just like we can take it as like pod is a container. So the pod is running inside one node. There we bind, or the Kubernetes cluster volume plugin, mount the volume, fuse mount the volume. Then it make use of the Docker feature like bind mount. It bind mount the volume to the container, so that when the application pod store the data inside the bind mount volume, you are basically store it inside the persistent store. Is that clear? I hope so. So let me invite Luis back to stage.
All right, thank you, Humble. So now that we have these technologies, we have OpenShift, we have Kubernetes, and then we have Gluster. So what the administrator does, this is a typical architecture of their deployment. They have a set of OpenShift masters that they have here, and then they have a set of OpenShift nodes. OpenShift nodes could be anything from VMs to blade systems or anything with small amounts of storage, or just enough to boot. Then, for example, they have same nodes, still part of the cluster, still can run containers, application containers, but those systems have disks. And what the administrator can do now is they can deploy Gluster as an application, just a normal application, just like anything else, into these OpenShift nodes with storage on them. So what happens now is that from the single client, the administrator can deploy not only applications, not only software-defined networking that's done to manage all this, but also the storage. So now, as you can see here from the stack, you see cluster 0, 1 to n. So you're probably thinking, okay, how can we manage all those systems, create those volumes, and how are we going to satisfy those requests? Well, the next part is the volume manager that we have. We call that Heketi. And what Heketi is a service for services. Okay? So what it does is that it presents a REST interface, and it allows the administration of any number of GlusterFS clusters. And what it does is it's like a storage manager. It manages all your disks in those storages, and then after that, it can service requests for volume creation. Okay, and not only that, but you're probably thinking, okay, does it have mount points, or are they created already, or where are the bricks? Heketi takes care of all that for you. It has algorithms to determine what bricks to pick in the cluster, how to create the bricks, what file system to put on them, and then after that, how to delete them and bring them back to the pool. So let's take an example of just the simple architecture. Again, Heketi is not extremely complicated piece of software. It's just how does it do it? It has just a simple RESTful interface, and it has what we call interfaces at the bottom. The executors allow Heketi to be able to communicate with Gluster and send commands to the systems and the nodes. For example, when we first had Heketi back when we were working OpenStack Manila, we used what's called the SSH executor, which allows Heketi to SSH into a system and send commands there. What we had to do for Kubernetes is that we couldn't SSH into a pod, because then that would mean that each pod would have an SSH port. Instead, what we do is that Heketi sends an RPC command to Kubernetes and says, I want to talk to this pod. And then Kubernetes sets up what's called a SPDY connection between this pod and the GlusterFS pod. That way, Heketi can send commands to that pod specifically and run commands like makefs, LV commands, PV, create, and such. And then we have this thing called the allocator, which we'll go into a little bit, and that's how it determines what what devices to pick through the cluster. So when it allocates, for example, a set like a replica 3, for example, it picks a device on somewhere on the system, and then it makes sure that its replicas are not on the same failure domain. So let's take a look at how Heketi is set up first. So here's an example of what Heketi does. We have first, let's pretend we are an administrator, and we are going to create just a couple of clusters. And clusters in Heketi is just a grouping of nodes. That's all it is. It's just a collection of nodes. So we create 2 clusters, then we add a node. When we add a node here, the very first thing we do as we add nodes is that we say the management IP address of the node, the storage IP address of the nodes, but most importantly is the failure domain of the node. And this is very important because Heketi needs this information to be able to calculate where to place the replicas. So the more zones there are, the better it is for the replicas to have survive a failure. So what is a failure domain? A failure domain is whatever the administrator feels that is. For example, it could be a few machines share the same power supply, or they share the same switch, and so on. So we added a single node to Heketi. We say, here's this node, add it. So when we add more nodes, as we add more nodes, Heketi automatically starts doing the peer probes. So the first one didn't need a peer probe because it's just one. The second one comes in, starts doing peer probes. And such, in this one cluster that we have here as an example, we have a trusted storage pool created automatically. So in this step, we have no devices. There's no storage for Heketi to manage. If you ask for a volume, it'll say, I have no space. But what we have to do now is register the drives on those nodes with Heketi. It doesn't go out there automatically and starts picking drives just, because it could pick a drive that you wanted it not to use. Instead, you specify which of the drives in those systems it can use. When it goes and you tell it a drive, and it has to be a raw device, not a file system, okay? And what it does is that it creates a PV on that disk, across the entire disk. And then after that, it creates a VG on top of that. That's all it does. So when you tell it a device in some system, it has to be a raw device, PV and VG. And why does it do that? Because when you ask for a volume and it creates bricks, what it does is that it creates a thin pool of some size, depending on how much snapshot space you would like. And then it creates an LV on top of that and an XFS brick. So that's how it handles the ability to make sure that the systems are not fragmented with spaces and things in between. So it tries to make sure that it matches and creates the brick sizes for the request that comes in. So when you get a request for 100 gig volume distributed, it creates, for example, distributed replicate. 2, it will create 50 gig XFS bricks. So you guys can ask any questions any time, so don't feel that you have to wait till the end. So here's an example also of Heketi managing multiple clusters. So not just it can manage one cluster, but it can manage multiple, it can manage n number of clusters. So for example, when you send a request to create a volume, the REST interface allows you to say, okay, I want you to create a volume from anywhere. I don't really care, just pick one. And then Heketi will go and find your volume. Or you could say, I want you to create a volume for me from this subset of clusters. Maybe those subset of clusters have SSD or SATA. And so again, you gotta remember that Heketi is not supposed to be created for the user to be used, but for services. So those services may have, for example, in OpenStack, they have what's called classes of storage. You can have gold, and you have silver and such. So you could divide the clusters into those modes, and when the user actually requests a gold one, the request come to Heketi and say, this is what gold means. It means these sets of clusters. Pick a volume from there for me. So let's take a look now how it organizes the information from the topology of the cluster to satisfy a request of creating a volume. And it is kind of based on the technology from Swift. If you understand how the Swift ring works, and it organizes all the replicas and the zones and the failure domains and such, what it does is that it takes the entire set of devices on a single cluster. So this is done, there's a ring for every cluster, and it organizes that ring in such a manner that as it moves through the ring, there's a device from every zone. There's not two zones the same zone put together consequentially in the ring. So as you can see here, we have zone 3 as we move through the ring, zone 2, zone 4, zone 1, zone 3, and so on. And it tries to make sure that the zones are as far away from each other in the ring, and the nodes also. So as a device comes in, we don't start again every single time from 0 on the ring. What we do is we hash a device, a brick name, and somewhere we put that brick into the ring pointer, and then we start the array from there. So that way it kind of randomizes where it starts on the ring. But the interesting thing is that this data is calculated at every creation, so it's not static. One of the things that we had to do when we first started the Heketi project, and again, we were basing it on Swift and seeing how it did it, we couldn't exactly use Swift's ring because they pre-calculate that. And it takes a long time to pre-calculate that ring. And then we needed a method that we could calculate as the state of the clusters change, which could change any second or any millisecond. So what we needed to do is we needed an algorithm to be able to calculate this in an extremely fast way. So this is done as the state of the system is at the time of the request. Okay? There could be devices. Heketi supports the ability to maintenance systems. So if you want to say, like, I want to maintenance this node, please don't allocate any new volumes in that system. So those devices on that node will get removed from the ring for that period of time that you asked. So now, let's go continue the creation of the volume. And what we have here is that Heketi has picked a device to create a brick from the first node on zone 1. And its replica was found to be on zone 2 on node 2. Okay? And so on, distributed. This is distributed volume in this example. And again, first brick on the node 2 on zone 1, and then the second on node, I think it was, on node 1 on that specific drive on zone 2. But again, on the same zone, on the same cluster. So that's how Heketi works. And we have a demo to show you right now. And the demo is as follows. We take all these technologies what you showed you, and we kind of put them together. And we have a set of VMs in this demo. And we have 5 VMs. We have 3 OpenShift nodes with storage on them, 3 drives each. And then we have the OpenShift master. And all that you're going to see is done from the single client. Okay, we're going to deploy the storage, we're going to use the storage, we're going to deploy an application. So here we go. All right. So the first thing is that we get the nodes in the system, we find out what the nodes are. Yeah, thank you. And I just wanted to let you know that, go ahead just a few more seconds. This right there, we just deployed 3 nodes of GlusterFS, right there. That's how simple it was for us to deploy as a container. And now, but I just want to let you know that when we deploy the containers, they're just sitting there. They're not part of a pool, they haven't been set up. Their containers running GlusterD, and that's it. They just start up, and they're running GlusterD, and they're at that state, waiting for the next step. What we're doing here is that we're going with deploying Heketi. It's a bootstrap Heketi. It kind of, the way it has all the state is kept on a database right now, and we may think of moving that into XCD so we don't have to do this multi-step. But right now, it's sitting on a single file database, and it's not safe. So what we're going to do is that we're going to create everything, then we're going to create a GlusterFS volume for the database, and then we're going to restart. Okay? So right now, what we do is over here, and as we can see, is we have the GlusterFS systems running on 3 different nodes, and that is done by something called node selector. So normally in Kubernetes, you don't have no idea when you're going to run. But you can tell Kubernetes, if you know, say, I want this container to run on that system only. So that way we can pin down that container into that system. So that's what we do. We pin down these GlusterFS containers into those systems. And then we have the bootstrap Heketi, which can run anywhere, it doesn't matter. So let's continue on. And then what we do now is, Heketi doesn't know anything. We say cluster list, has no idea. It's like, nothing, I have nothing for you. So as we continue on, the next thing we need to do is provide it with the topology. And we have set the entire topology of the system through this one JSON file called GlusterFS topology.json. It describes in it the nodes, the devices that we need to add. So we're going to go here, we're going to load this. And then Heketi is going to go into the system. It's going to initialize the devices. And then the second node, and that's a peer probe. And then the devices again, that's PV and VGs created. And then again here, for the third node. And again, just to let you know, I'll just pause it here. the Heketi not only can be used for containers, and the we're almost done. Yeah, and then, but it can also be used without containers. So it can support replica 2, replica 1, and 3, and EC. We're going to add in the future striping and what's the one with 2 and 1? Yeah, arbiter. And then we're going to add to that later. So let's continue on. You can just let it run now because we're almost out of time.
Okay.
So here what we do is that we say cluster list. We have the cluster that we created, and what we have here next is we're going to set up the bootstrapping method, which it creates the volume. We're going to use OpenShift services to be able to copy the database from where it is right now, which is not safe, into a GlusterFS volume. So as you can see here, we didn't do the actual copy ourselves. We used all OpenShift services and Kubernetes services to be able to do this. And the next thing we're going to do after this is that we're going to delete the bootstrap. We're going to start up the real Heketi system with the database on the GlusterFS volume. From now on, that's safe, right? Because Gluster is awesome, right? So, and then what we're going to do now is we're just going to set a simple variable here, so we don't have to type the server address anymore. Cluster list, we had the same cluster as before. And here's the big part. All we say here now is we don't specify what system, we don't specify what bricks. We just say, I want a volume of 100 gigabytes. That's it. And then we ask the CLI for a little more help. It's like, could you also create for me a Kubernetes persistent volume so I don't have to do it, all right? And then put this in there for me. So all of those things are just the command line doing that for you. A little more help. But the key thing here is the size of 100 gigabytes. So we do this and we pipe it right into OpenShift, and it goes ahead and registers that volume with OpenShift. It is now available. So any user can come in and say, I want 100 gig volume, and that will be the volume that they get. So just for the demo, let me just go a little bit faster here. For the demo, what we do is that we mount the real volume, it's a real GlusterFS volume, on the client. And when we mount it on the client, what we're going to do is write a file into it called I love GlusterFS as index.html. Okay? So we're going to write it into the root of the volume, and then what we're going to do here is that we're going to look at this application. Here's what the user would do. This application has what's called a service, meaning that I want this application to have a TCP connection. A route, meaning I want this application's TCP connection to be accessed outside the cluster. And then, yeah, go ahead, thank you. And then, here's my claim. I want this application to have 100 gigabytes. And then, I want that 100 gigabytes to be mounted, go ahead, in this location right here. And now you can just let it go, it's almost done. Thank you. And then, here what we do is we register the application. It creates all these things for us. Somewhere in the system is running. And what it does is that we have now bound that claim into the volume. And then right here, we curl it and we say, I love GlusterFS at the bottom. Okay? So that's as simple as that. And that's the simplicity of using this system. Users can go ahead, create a single description of what they want. And it is deployed automatically in the system and is serviced by the system. So let me go back to the presentation, and there's one slide more. So where do we go next from here? Whoops, I did it backwards.
Yes, it's fine.
So Heketi right now doesn't have failure support. So what that means is that you can take a drive, for example. When do you do replace break? Like a drive dies or a node dies or something like that. So what we need to do is the ability for an administrator to point to a drive or a node and say that node is dead. It's never coming back, so do something about that. So what Heketi will do is at that point is find new bricks automatically in this cluster and automatically do the replace bricks for you. Second is full Kubernetes support is coming in. I think that should be in by today or tomorrow. Is the ability to communicate with Kubernetes a little bit better. And then again, we're talking about storage, which we just did, the iSCSI stuff. We have a proposal to have an API in Heketi to be able to ask for block storage. So not just volumes, but now block storage also. Lastly, in Kubernetes itself, we are also working there to be able to have something called like dynamic provisioning. As you saw before, that from the command line we created the 100 gig volume. But it will be so much easier if when you create the claim, it automatically creates the volume. So that's called dynamic provisioning, and that is actually coming in this version of OpenShift. And then just an easier way to deploy. Right now we're working on that still. Just a few steps. But if you want any more of the information, we have a wiki page, demos and everything, and also a Vagrant demo. You can try all of this yourself on the Heketi GitHub webpage. Okay. Any questions?
I'll pick that back. It's fine.
Please. Oh, sorry.
I'll turn it off.
I turned it off, yes.
So when you run normal applications on containers, so the orchestrator can schedule them on any node because they have no affinity to particular nodes. But when you come to cluster, the orchestrator has to schedule that only on particular nodes that contain the bricks.
That's right.
And you also run container in a privileged
That's
mode.
right. Yeah.
So is there any reason why you would want to run cluster inside a container and not outside of it?
Yes, absolutely. As you saw there, it only took a few seconds to deploy Gluster. So the whole idea is that so Bobby everybody needs the mic, just like you. The whole idea is to be able to manage the Gluster system. You gotta think like not like a storage manager, but you have to think of like the compute administrator. The compute administrator is not very knowledgeable on storage. He doesn't want to learn about that. He wants to deploy it, he wants to be managed. This is a way for this OpenShift Kubernetes administrator to not worry about the storage management, to just deploy it like any other application that they know how to deploy. And not only that, but they don't have to set up how many nodes, a separate system to be able to run Gluster. They don't have to set up how many 10 gig systems. They set up their same systems that they use, just happen to be that they run Gluster inside. That is a much easier deployment model for those administrators and management models. So again, it's not to say that this solves everything for everyone. This is a model for those running applications as containers, and they want to manage those that storage systems through the same user interface that they already manage their compute.
Is Heketi itself highly available?
Heketi itself highly available. So, does it need to be? No. No, it's not highly available. No, the database is the only point of that it needs to be persistent, and Kubernetes actually takes care of the high availability for Heketi by if any time that it dies, it restarts somewhere else in the system. So Heketi itself, if you're running it by itself, is not HA, but I would say that with Kubernetes it is, and because you can access it that same, the service. You're thinking that whenever time I talk to the IP address of Heketi, that is always available. It doesn't matter what node it goes to and moves to. And the Gluster first volume where the database is always attached. Doesn't matter what node that Heketi container is running on. So does that answer your question?
So Heketi or Kubernetes is starting Heketi.
Yes.
And managing it.
Yeah.
It is also calling into Heketi to service dynamic provisioning requests or whatever.
Right.
And Heketi is calling back out to Kubernetes to satisfy those by starting other containers and such. Is that right?
No. Heketi doesn't call back to Kubernetes to start containers. Heketi only calls back to Kubernetes when a request comes in to talk to Gluster first containers. It's just a channel. It's just a pipe. So it's a tunnel.
We can either do more questions or we can go to lunch. Lunch? Lunch.
Yeah.
All right, lunch. Scratch
Thanks,
them
guys. Bye.
all.